Hello everyone, welcome to the second day of the PC 301 workshop, and we start with our first talk of the day, and we have with us Roohani Sharma from Max Planck Institute Max Planck Institute for Informatics, and she'll be speaking on kernelization. There'll be more talks on kernelization. This is the first one in the series. So thank you for joining us, Roohani. Over to you now.
Thank you for the invitation. So as Pratibha said, this is the first talk in the kernelization series, and there'll be two talks totally. And let me begin by saying that kernelization is definitely one of the ways of designing FPT algorithms. Like you saw some techniques yesterday, iterative compression, probably branching, color coding, and other randomized methods to design FPT algorithms. Kernelization is definitely one of them, but it's much more than a tool to just design FPT algorithms. And so much so that there is now a full textbook devoted to this area of kernelization. And we'll touch upon this aspect of what makes kernelization so special compared to other techniques to design FPT algorithms, but we'll do that as we go along. So the rough outline of the talk is as follows. So we'll begin by seeing where does this idea of kernelization stems from, slowly followed by sort of a semi-formal definition of kernelization, and it'll be followed by essentially some example problems. We'll pick up some problems and try to design kernels for them. And that'll be essentially what I'm gonna do today. So let's begin with where does this idea of kernelization stems from. So this stems from a very fundamental idea of preprocessing. So preprocessing is something that is someone's natural tendency when they see a hard problem. So whenever we see a hard problem, a natural tendency is to see if we can chunk out pieces of this hard problem as much as possible so that we only have to deal with a very small hard problem. Like a toy example of that would be, imagine a student deciding to prepare for an exam just a night before the exam, and he or she has lots of syllabus to cover. And at the last minute, at the last night, the student needs to make some calls as to what topics to leave and what to read in order to survive the exam. And then as a student, we start coming up with some sort of heuristics. Like, for example, maybe you know the teacher very well, and the teacher asks some topics in the class test maybe a month ago, and then you're fairly sure that the teacher does not like repeating the questions, and maybe there's a good chance he or she won't ask the same set of questions again this time, and then you end up like scrapping off those topics and moving forward. And then maybe you apply another heuristics, like maybe there are some topics which have been covered in every exam probably for the last 10 years, and this year being no special year, though that's not the case with 2020, but in case this is no special year, you expect the same sort of question to be asked again in this test, and then you end up preparing that very well, and probably you apply some other heuristics to shorten the syllabus, and maybe at the end you also have lost hope to excel in the exam, and you're only probably aiming towards getting a pass mark, maybe a pass of 50% marks, and then maybe you end up applying some sort of pigeonholing principles over the set of important topics to further shrink the number of topics that you need to cover, right? So, and maybe at the end of it, you actually survive reading up what you think is a set of important topics, and maybe you end up surviving the exam also by doing this. But this is all heuristics. So if you are lucky, you do fairly well in the exam and you survive it. But in adversarial situations, luck might not just favor you. And we as theoreticians are interested in doing whatever we do with guarantees. So we want to do something, but then we want a guarantee for that, unlike heuristics. So, but it seems that this idea of preprocessing, where we are interested in shrinking the size of the input, this idea one might be suspicious in if someone says that this idea can be applied to hard problems for us, NP hard problems, and still in the sense of the guarantees that we want. So let me formalize this in the next slide. So let's say pick your favorite NP hard problem, and let me ask you, and I ask you this question, can you decrease the size of your instance by, let's say, 1% or 0.1% or 0.000001%, and do this in polynomial time? So you have an NP-hard problem, I give you polynomial time, and I just ask you probably to reduce, let's say, the size of the instance by 1 bit. Can you do that? It shouldn't be the case, because if that's indeed the case, you start with this big instance denoted by this black instance, you spend some polynomial time and end up eating something out of it and just shredding it out of the instance. And you keep doing it, you spend another polynomial time, shred out further part of the instance and keep doing it, and before you know, the instance is actually vanished and you've just spent polynomial time. So that means you've ended up solving an NP-hard problem in polynomial time, and this shouldn't be the case unless, of course, you believe that P is equal to NP. So, but does this mean that it is a dead end for applying pre-processing for NP-hard problems? It turns out no. Probably we are not asking the question in the right way. And let me now elaborate on what I mean by this. And let me elaborate it by means of an example first, and then I'll formalize this. So this is now a little serious example, like not like the toy example we saw before. So this is a problem called the point line cover problem, and it's defined as follows. So the input is a set of n points on a plane, and you're given an integer k. And the question is, you want to draw some k straight lines, not line segments, but lines, such that every point, each of these n points lie on at least one of these lines, right? So you have n points, and you want to cover each of these n points with k lines. Like these, let's say this is the set of points that you have on the plane, and let's say I want to see if they can be covered using 3 lines, and they can be indeed. If you look at the red lines, they cover all the points. So this is the problem that we're interested in, and this problem is indeed an NP-complete problem. And now we want to see if we can reduce the size of this instance. And by size, we mean we're given n points on the plane. Can we do something in polynomial time and shrink the number of points in the given instance? And our motivation, given that we are sitting in a parameterized complexity workshop, our motivation for doing what we're going to do ahead is the following. Let's say that we are given 100 million points in a plane, but we want to cover them by just 10 lines. Then k is and k is 10, and we want to see that do we really need to keep all those 100 million points in an instance to just check if they can be covered with 10 lines. And this is the motivation with which we start to design pre-processing rules for this problem. And in order to think about to start thinking about how do we come up with rules, pre-processing rules, I think one good way of a good starting point is to think as follows. The input instance is very large, and the number of points is very large, and we are only interested in yes instances. So just concentrate on an instance that has lots of points and which can indeed be covered by 10 lines, let's say. So how will those instances look like? So towards that, observe that if you look at any one line, it can cover sets that are collinear. So any line passes through a set of collinear points. So any line can cover a set of collinear points. So if it is indeed a yes instance, we know that the set of points can be partitioned into at most k collinear sets. So you can partition into at most k sets such that each the points in each set are collinear. So there are not a lot of, so you can actually partition the number of points into a small number of sets, but now the problem is that each of these collinear sets is very large. And now you want to design some rules that can bound the size of these collinear sets. And so the size of the collinear sets is large, and now we know what we want to do in order to reduce the size of the instance. We precisely want to bound the size of large collinear sets in the graph, right? And this should not be difficult because, let's see. So let's say you have a set of k plus 1 collinear points on collinear points. Then you know that any solution that uses only k lines will have a line passing through all of them, because if the blue points here are let's say the k+1 collinear points, and now if I don't assign a line to these collinear points, then the only way to cover these points will be to have one line each passing through each of these points. And since the number of points is at least k+1 and your budget is k, you can't have that. So any k-sized solution, any k-sized set of lines needs to devote one line to cover all the points which are collinear to these points. So you draw this line, you decrease the budget by 1, and you remove all these points from your instance, right? So after that, and you do it repeatedly over and over again, as long as you have some k+1 collinear points in the reduced instance. And once you do that, you notice that now the size of the collinear sets is at most k. The size of any one collinear set is at most k. And now let's say after you've applied this preprocessing rule, and let's say now you're no longer able to apply the rule. Let's say the number of points in the resulting instance is n prime, and let's say the budget has been dropped from k to k prime. Then if the number of points are still more than k prime squared, then it's definitely a no instance, because any line now, because there are only every collinear set now has size k, and if there are lots of collinear sets, then you cannot cover them using only k prime lines, right? So with this preprocessing rule, we have by an application of this preprocessing rule over and over again, we have reduced our instance from n points to at most k square points, right? So and this is not under any heuristic, this is very deterministic. Whenever you see k+1 points, you can indeed throw them away and decrease the budget by 1. And this is very deterministic, and there is a guarantee involved in the preprocessing rule that we have designed, right? So what has happened here, and this was an NP-complete problem, so we have guaranteed to decrease the size of the instance by something, even when it was an NP-complete problem. So what has happened here is that we have decreased the size to k square, but this decrease happens only the decrease is considerable only for smaller values of k. So if k itself was very large, then you do not really decrease it. So there is a threshold until which you can pre-process these NP-complete instances, unlike our previous notion of pre-processing, where you could just go on and on and on until the instance completely vanishes. So this sort of preprocessing is called kernelization in the world of parameterized complexity. So let me sort of define kernelization a little formally. So for me, kernelization is, in one line, it is efficient preprocessing with guarantees for parameterized problems. So let me explain each of the terms in this phrase. So it is efficient, meaning it's an algorithm, it's a preprocessing algorithm that is efficient. By efficient meaning it runs in polynomial time. So throughout the talk, whenever by n, I denote the size of the input instance. And it's a preprocessing for parameterized problems. That means it takes as input a parameterized problem, which consists of an instance I together with a parameter k. And it's a preprocessing algorithm. That means it takes this input, it takes this instance of a parameterized problem and returns an equivalent instance of the same parameterized problem. Let's say the equivalent instance is I prime k prime, with a guarantee, and the guarantee being that the size of the resulting instance is bounded as a function of the parameter of the original instance. So in this case, the resulting instance size prime and k prime are some function of k alone. They do not depend on the size of I. Right. So this is a formal definition of kernelization. So it's basically a preprocessing, it's basically a polynomial time algorithm which does this. And in case a problem pi admits such a kernel, we say that admits such an algorithm, we say that it admits a kernel of size gk, where gk corresponds to this size of the resulting instance. And if gk is a polynomial function of k, we say that pi admits a polynomial kernel. And if gk is an exponential function of k, we say that it admits an exponential kernel. Right. So this is what kernelization is for us. So any doubts so far?
Yeah, sorry. So I sent you a question on the chat.
Okay, sorry. Let me see if I can see chat here.
Hi, Roohani.
Yeah.
So yesterday, Mikhail Pilubjuk applied one very nice trick. So you can put this in the chat. You can say, you can ask people that if they have understood to put +1 whenever you wish. Then people put +1 if they have understood. And if not, they ask question. So this way you will have some feedback mechanism and that will help you go forward.
Sure. Okay, good. So as Saket says, please participate in the talk, and please write +1 if you're following up. And if in case there are doubts, please feel free to mute yourself or ask the question in the chat. Okay. So I see some +1, so everything's fine so far. Thank you for responding. So let's proceed. So this is what kernelization is, and let's now go over another example.
Sorry, one second.
Okay.
So I raised a question like before that regarding the time taken to find the collinear points. I think I sent it to this queue by mistake. So let me just repeat the question.
Yeah.
Yeah, I've sent it now.
So note that this can be done in polynomial time to find. So you just need to see if 2 points lie on the same line. So using this line equation, y = mx + c equation, the standard equation, this can be done in polynomial time. That's not hard, and that's a good question. Yeah, it should be done in polynomial time.
So, but if you have k many points, you have to find all. I mean, set of all points which are collinear, correct?
No, but know that so you just need so you need to check it for 3 points, right? And then you need to see so now for those 3 points you'll get a line. You'll get a line segment, and then you just need to check if what all points lie on that line segment to see what all collinear points are there. Or in other words, you can think of it like this. So there are n points. You can think of as having an initial space of n squared lines, because for every 2 points you can have a line passing through them. And now for each of these lines, like one trivial way is for each of these lines, you just check which other points lie on this line to see which points are collinear with this pair of points. Is that fine?
Yeah, okay, that's fine.
Thank you. So yeah, so before proceeding further, so with this definition of kernelization that we have, note that what we indeed did for PLC was the point line cover problem was that we proved that it admits a kernel of order k² size, or it admits a kernel with order k² points, right? So let's now proceed to the next example, and this is called the edge click covering problem. This is again a sort of a covering problem like the point line covering problem, but here you're trying to cover the edges of a graph with the cliques of a graph. In particular, the input is a graph G and an integer k, and the question that you want to ask is, does there exist k cliques in a graph, let's say C1 to Ck, such that for any edge uv in the graph, there exists a clique that contains it. So an edge might be present in lots of cliques, but there is a guarantee that there is at least one clique that covers this edge. So for example, consider this graph that we have. So let me put the first 3 vertices in the orange box as one clique. So this is a clique on 3 vertices. So this is one clique. It covers the edges of the triangle inside the orange part. And now let me now have a second clique, which is denoted by the 4 vertices in the yellow square, and so on. The green clique, the purple clique, the pink clique, and the cyan clique. So if you notice that all the colored boxes denote cliques, and all the edges are present in at least one of these colored blocks. So this is so now we're interested in seeing if this problem can be kernelized. And let's see let's start to design some rules and see what kind of rules do we need. So given this example, it's clear that these isolated vertices that are sitting here, they really don't have any role to play. So we could as well delete these vertices because there are no edges incident on them. So we delete these isolated vertices. And then we look at this connected component, which is a clique in itself. And we know that to cover this clique, I need one full, to cover this connected component, which is a clique, I need one full clique in the solution. So you delete this whole connected component, that's a clique, and decrease the budget by 1. And you keep doing it until you can no longer do it. And after that, you have a graph like this. And again, now the idea being, we know that the edges of the graph can be covered by k cliques. So now the reason that the graph is very large is because these k cliques are very large, right? And now somehow we want a mechanism to bound the sizes of these cliques. And one very nice trick that's used in fact a lot of other kernelization algorithms also is this. So you look at two vertices, let's say U and V, and just look at the neighborhoods in the graph, the close neighborhoods in their graph. So if their close neighborhoods are the same, so if you look at these two vertices UV, if you look at their neighbors, they have these three vertices as neighbors in the graph, and they have exactly these two vertices as neighbors, and they also have an edge between them. So the close neighborhood of these two vertices is the same. In this case, the rule is that you go and delete this one of these vertices. Let's say we go and delete U from the graph, right? And now we need to show why is it okay to do it, or why is this pre-processing rule, or we call them as reduction rules also, why is this reduction rule safe? Why is it okay to delete such a vertex? And to see the safeness, one sees that, okay, if one need to show that the resulting instance is an equivalent instance, and for that, you look at the original graph. If the edges of that graph could be covered with k cliques, then we know that the reduced graph in this reduced graph, you can use the same cliques to cover the edges of the reduced graph, because the edges of this reduced graph are smaller than the edges of the graph that you started with. So this direction is fine. But now what happens? What if you give me some k cliques that cover the edges of this graph, the reduced graph? Now I need to give you some k cliques that cover the edges of the original graph also. And let's see how we do that. So let's say I give you these k cliques that cover the edges of this reduced graph. Now the idea is the following. I look at the cliques in which this vertex V is present. So V is present in this clique purple and green. So V is present in these two cliques. I go and put U in the same cliques in which V was also present. So this vertex was U. I go and pick U in clique green and clique purple. And the claim is these cliques now cover all the edges of the original graph. And that's true because if you look at the vertex, if you look at the neighbor set of V, the neighbor set of V is precisely the set of neighbors, is precisely the set of vertices that are present in the cliques that contain this vertex V. So the neighbors of V cannot be anywhere else. And now, because the neighbors of U are exactly the neighbors of V, we can put V in the same cliques as we can put U in the same cliques as V and get the desired clique covering. Right. So this is the so this rule is indeed safe to do. A little caveat note that it might happen that so we delete U, and now maybe V now is deleted because V's neighbor was equal to some other vertex W's neighbor, and so on. But note that for any vertex V that's deleted, we have at least one vertex. For any vertex U that's deleted, we have at least one vertex in the instance. If not, then if we end up deleting all vertices that have the same neighborhood as V, then note that those set of vertices will form a clique in the whole graph, and it will be a connected component, which is a clique. And in that case, we would have applied the previous reduction rule. So we always have a witness for U in the resulting instance. So this rule is indeed safe. And now we just apply this rule exhaustively. Now we look at these two pink vertices. They have the same neighborhood. We delete one of them. And now find another two vertices which have the same neighborhood, delete one of them, and proceed until we get this graph where none of these rules are applicable. And let's say, and we call this as the reduced graph. And let's say the number of vertices in the reduced graph is n prime, and let's say the budget has dropped down to k prime. And now there is this rule that says that now you just look at the vertices of the reduced graph n prime, and if the number of vertices is at least 2 power k prime, then it is a no instance. And let's say why that's the case. So let's see why this rule is safe. So if not, suppose it was not a no instance, if it was a yes instance, then there exists some cliques C1 to CK. And now given these cliques, for every vertex, let us assign a 0,1 bit vector to this vertex of length k prime. And the bit vector is like this. The ith coordinate of the bit vector is 0 or 1, depending on whether that vertex is not present in clique Ci or present in clique Ci. So for example, if you look at this vertex V, which is here, this vertex is present in orange and yellow cliques. So I have 1 for those coordinates and I have zeros for the others. And note that the number of 0,1 bit vectors of length k prime is equal to 2 power k prime. Also note that if a vertex was isolated and we have removed all isolated vertices, those vertices will get bit vectors all zeros. And now we want to see, now we are interested in seeing how many vertices are there in the graph, and we have assigned a bit vector to each vertex, right? Now the claim is that no two vertices can share the bit vector. Note that if we show this, then we are done, because the number of bit vectors is strictly less than 2 power k prime, because the 0, 0, 0 bit vector is not available because we have deleted isolated vertices. And if every vertex has a unique bit vector, then the number of vertices cannot be more than 2 power k prime. And now why is it the case? Let's say if there are two vertices with the same bit vector, look at these two vertices, look at the cliques in which they participate. So they participate in the same cliques, right? And as I said before, the neighborhood of any vertex in the graph is precisely the union of the vertices of the cliques in which it participates. So if two vertices participates in the same set of cliques, then those two vertices will have the same neighborhood, right? But for those vertices, we already had a reduction rule before. So we have already taken care of these vertices, right? So every vertex has a unique bit vector, and hence the number of vertices after the previous reduction rules have been applied is strictly less than 2 power k prime. And this gives us a kernel for the edge clique covered problem with 2 power k vertices. So again, any doubts? So we have finished the edge clique covered problem. Again, please put a +1 if it's clear, otherwise you can put. Okay, good. So before moving forward to other examples, let's talk about some lighter things, lighter yet powerful things. I talked about this relationship of FPT with kernelization. And as I said in my first slide, kernelization is a very special child of FPT. It's not like any other technique that is used to design FPT algorithms. And the reason is as follows. Kernelization, of course, like any other technique, if you have a kernel, you get an FPT algorithm out of it. And we'll see, it's not difficult, but we'll see it in the next slide. And but it's the other way around is also true, that if the problem is FPT, then it indeed admits a kernel. Like this is not true for the other techniques you saw. Like it's not always the case that if the problem is FPT, then there is a branching algorithm that solves a problem, or there is an iterative compression algorithm that solves a problem. You might not say statements like this for every FPT problem, but this is true for kernelization. And let's see why. So what I said before is that a parameterized problem is FPT if and only if it admits a kernel. And one direction is trivial, because if, let's say I give you a kernel of size f of k, then you can design an FPT algorithm for the problem like this. So you find a kernel in polynomial time, and then you brute force over this f of k size instance. This brute forcing, in this brute forcing, you'll spend time proportional to k, and let's say gk. And as Saket mentioned in the very first lecture, this is also an FPT time. So if the problem has a kernel, it is FPT. The other way around is also true. So I want to say that if the problem has an FPT algorithm running in time f of k into poly n, so there is an f of k function, then it has a kernel of size f of k. At least it has a kernel of size f of k. And this powerful thing is actually very simple to prove. I don't know if Saket already did it in the first lecture, but if he already did it, let's just still revise it. So let's say you have an FPT algorithm running in time f of k n power c, and you check if the function f of k is less than n. Then in this case, note that this whole running time is just n power c plus 1. So this is the FPT algorithm is in fact a polynomial time algorithm. So you can use that as the kernelization algorithm, solve the problem, and return some trivial constant size kernel for the instance. And in the other case, f of k itself is much larger than n, or in other words, n is strictly smaller than f of k, in which case you get a kernel of size f of k. Right. So if the problem admits an FPT algorithm, it definitely has a kernel. And also, because we talk about NP-hard problems, typically the FPT algorithms that we would develop will have exponential f of k factors, at least super polynomial for sure, right? And hence, if the problem is already proven to be FPT, it definitely has some super polynomial or exponential kernel. So for problems that are proven to be FPT, typically we are interested in designing polynomial kernels for the problem. So the design of polynomial kernels is in itself a very integral subfield of parameterized complexity, right? So in what follows, let us try to design some polynomial kernels for some problems, some more examples. And it can never be fair to skip the problem vertex covered in any of the parameterized complexity lectures. So even though Saket covered the vertex covered kernel in the first lecture, I'm going to repeat it again. And there's a reason why I'm repeating it, and we'll see it in a few moments. So again, I'll quickly go over the vertex covered problem. You're given a graph G, an integer k, and the goal is to decide if there exists at most k vertices such that every edge of the graph is incident on at least one of the vertices of this set, right? So this is the problem, and we have already seen reduction rules for this problem. For example, the first reduction rule says if there is a vertex which is isolated, which has no degree, then just delete it because this vertex is of no use for us. And then the second rule, which is a very crucial rule, this is also called the Buzz rule because it was given by Buzz. So this rule says that if there's a vertex of degree at least k plus 1, then this vertex needs to go to any solution of size at most k. And in fact, for vertex cover, if we know a vertex has to go to a solution, then we can as well remove this vertex from the graph and delete and decrease the budget by k. So we apply this rule, and at the end of the application of both these rules, let's say the reduced instances n prime vertices, m prime edges, and k prime budget. In this case, the next rule says that if n prime is strictly greater than k prime squared plus k prime, or m prime is strictly greater than k prime squared, then we can say no. And the reason why we can say that is because suppose the instance had these many vertices and edges and it was a yes instance, then look at the k prime size vertex cover of that instance. Let's let that be S. Now look at the number of edges in that instance. All the edges of this instance are incident on at least one vertex of the vertex cover. So the number of edges cannot be more than the summation of the neighbors of the vertices in S. Since the number of vertices in S is k prime and each vertex of S has degree at most k prime, we get this bound on the number of edges. Similarly, for the number of vertices in the graph is the vertices of S, and any other vertex, because we have already deleted isolated vertices, any other vertex is incident, has an edge, is a neighbor of S because S covers all the edges. So again, we get this bound on the number of vertices. So with this rule, basically, we show that vertex covered actually admits a kernel with k squared plus k vertices and k squared edges, right? And now, why did we do this vertex covered kernel again? But again, before that, I know I just repeated what was already taught to you, but again, any doubts here? If not, please put a +1. Okay, thanks. So let's proceed forward. So why did vertex cover now is because now we want to design a kernel for a problem that is a generalization of vertex cover. And we want to see if we can use the ideas that we had to design kernels for vertex cover, if those ideas can be used for these generalizations also. So that's the idea now. And let's proceed. So the problem is called the D-hitting set problem. Let me define this. So now we are moving away from the space of graphs to set systems. So now the input is a universe, U, containing some elements, and a family F, which is a family of at most D-size subsets of U, and you're given an integer K. And the question is, does there exist a set X, which are the elements of U of size at most K, such that X hits every set in the family F. So for every set S in the family, S definitely has some vertex of X in it. Okay, so this is the hitting set problem. Like, so this is how a typical instance looks like. So these footballs represents the universe. These are elements of the universe. I don't know if they're footballs or not, but yeah, some sort of balls. And these ovals represent the some subsets which are there in the family. And note that each of those ovals or circles that I've defined, each of them have at most 5 elements, the way I've drawn the figure. So this is an instance of 5 hitting set. And in fact, this instance has a solution of size 2, because if you look at, if I take this yellow ball in my solution, then it hits all these sets which I have colored yellow now. And now if I take another yellow ball, this covers the remaining, this hits the remaining sets. So this instance indeed has a solution of size 2. And it's not difficult to see that when D is equal to 2, this is the vertex covered problem, because when D is equal to 2, think of the universe as the vertices, think of the edges as, so the edges are 2 size sets. So you have, and they correspond to the edges of the graph. And now the goal is to delete, to see if there is a set of vertices such that each edge is, the endpoint of each edge is hit by the vertices of this set. So this is indeed the vertex covered problem. And so we want to see if we can design kernels for this problem for higher values of T, like for D equal to 3, 4, and so on, higher values of T. And to do so, let us try to see if we can mimic the kind of reduction rules that we had for the vertex covered problem. Like, what sort of mimicking do we need to do in order to get some, in order to get started with some preprocessing for this instance. Right? So let's try and mimic the buzz rule that we had for vertex cover. So the buzz rule for vertex cover says that if a vertex has degree k plus 1, then this vertex needs to go to the solution. Other way of looking at it is in the vocabulary of 2 hitting set, one can look at it like this. There are k plus 1 sets, which means k plus 1 edges, such that each of these edges has a common intersection point V, and these edges intersect only at V. And in that case, if you don't pick V, you have to pick each of the other endpoints of the sets to hit them. And since there are so many sets, your budget does not allow you to pick the other endpoints of these edges, right? So here is the rule for de-hitting set. We say, suppose there exists an element U, and there are some k plus 1 sets, S1 to Sk plus 1, such that each of those 2 sets intersect only at U. They do not have any other point of common point except U. And then in this case, we say that then in this case, the element U must go to the solution. So the picture here, the picture here looks like this. So these are the red sets, each of which have U in it. And except for U, if you look at the other vertices in the set, they're all disjoint. So this set has vertices V1, V2. This one has V3, V4. Okay, sorry. This should not be V4. No 2 vertices here can be same. So this is something else. Let's say V8. So if you have a structure like this, and now you're looking at a hitting set of size at most K, you know that if you don't pick U in the solution, then you need to pick at least 1 from each of these sets, and those 1 vertices are all disjoint, and hence you end up spending a budget of k plus 1. So in this case, again, you can delete U and reduce the graph. So this is exactly the same as the buzz rule that we had for vertex cover. But what we can do, but for d-hitting set, for higher values of d, we can do something more, and that is the following. It's the essence of it's the same as the previous reduction rule. So again, let's say we have some sets S1 to Sk plus 1. It's important that we have at least k plus 1 sets. So we have sets S1 to Sk plus 1 such that every two such sets in this collection have intersect at some set of vertices, which is C, and they intersect at exactly those C vertices, any two sets. So now in the previous rule, C, the size of C was 1, but now the size of C could be arbitrary. So if we have this, then the rule says, okay, in this case, you delete these k plus 1 sets from the graph and from the family F, and rather add the set C to the family. So the rule is like this. So you have, let's say, these sets, and let's say all these sets intersected at these two vertices U, W. And now since there are k plus 1 such sets, if you do not pick any of these two vertices, which are in the center, which are in the intersection UW, then you end up picking at least k plus 1 vertices to hit these sets, because these sets are disjoint at all places except for these two vertices, right? So hence we just need to remember that we need to hit these two vertices, and to remember that we can forget about these k plus 1 sets and rather just include a new set corresponding to vertices UV in the graph. And this is again a reduction rule. So as long as you find such structures in the graph, you can apply this reduction rule. And in fact, these structures have a special name for them. These are called sunflowers. So a sunflower is a collection of sets S1 to SR, such that for any two sets in the collection, they intersect at exactly C vertices, a collection of C vertices. And such a set C is called the core of the sunflower, and the core can be empty. So it could happen that I give you disjoint sets. So if I give you a collection of disjoint sets, they by default form a sunflower because they form a sunflower with an empty core. And the sets Si minus the core are called the petals of the sunflower. Okay. So this is the sunflower. So what this rule says is that as long as you have a sunflower with at least k plus 1 petals, you have some reduction rule to go for, right? So like in vertex cover, so in vertex cover, this sunflower corresponds to a vertex with degree k plus 1. We know that when you do not find a sunflower is when you're not able to apply this reduction rule. For the case of vertex cover, we know that in that case, if the instance was a yes instance, then the number of edges in the instance is very small. Both the edges and the vertices are small, and we got a kernel. So we need to design such arguments for the de-hitting set problem also. And these arguments are formulated in a very nice combinatorial structural result that's called the sunflower lemma. So the sunflower lemma says the following. It says that if you have any family with sufficiently many sets of size D, so when sufficiently many meaning some d factorial into k power d many sets, then this family definitely contains some sunflower with k plus 1 petals. So as long as your family size is bigger than this number that's written here, then you definitely find a sunflower with k plus 1 petals, in which case you can apply the previous rule. And when you can't apply the previous rule is when the family size is already bounded by at most d factorial k power d, in which case now we get a kernel because of the sunflower lemma. So if you use the sunflower lemma, we get a kernel for de-hitting set with these many sets. So note that I have written an extra factor of d here in the sets because there's a little technicality here. So the way I've written the statement of the sunflower lemma, it says that it'll be easier for me to prove that. Otherwise, the same holds for sets of size at most d also. But at least the way I've written this, statement, it says that you need a family which contains sets of size exactly d. So note that the hitting set instance can contain sets of size at most d at any given point of time, but that's not a problem because then you can always club together sets of size of same size and apply the sunflower lemma. And maybe you apply the sunflower lemma at most d times depending on the cardinalities of the sets. So you get an extra factor d here in the number of sets that you get in the reduced instance. And now that you have these many sets, you only need to keep elements that are present in these sets. And since each set has at most d elements, so you get these many elements in the reduced instance, right? So you get a kernel for d-heating set with these many sets and these many elements. And one key point to note here is that we get the asymptotic size of the kernel is order k power d, assuming d is a constant. So we have forgotten about the exponential factors of d if we assume d is a constant. So we'll prove the sunflower lemma just in the next slide, but I hope that if there is we have the sunflower lemma, then I hope it's clear that we get a kernel for d-heating set. Again, if you could put +1 if it's clear, then we can proceed. Okay, thank you. So let's now look at the proof of the sunflower lemma. And let me tell you that this proof in itself is it's a very nice result from combinatorics, and this has utilities even beyond parameterized complexity. So it's good to know the sunflower lemma and its proof. So this is the statement that we want to prove, and let's try to prove it by induction on D, the size of the sets. Right. So the base case is pretty fine because the base case happens when D is equal to 1. So when D is equal to 1, the size, you have a family F of size D factorial, which is 1 factorial into K power D, which is K. So you have a family of size strictly greater than K, and D is 1, so all the sets in the family are singletons. So in this case, note that you definitely have a sunflower with K plus 1 petals with an empty core, because K plus 1 singleton sets form a sunflower with an empty core. So D equal to 1 is fine. Now for the induction step, suppose I give you this. Suppose, let's see what is required to make the induction step go through. So one thing that's sufficient to prove is the following. Suppose I tell you that there exists an element V that is present in at least these many sets. So note that this number is precisely the number that we're trying to prove in the theorem for the value of, where the value of D is D minus 1. It's precisely the same number. So suppose I tell you that there's a vertex that's present in these many sets of the family. Then we are done, because you look at these many sets in which V is present, you delete V from each of these sets. Now you get a collection of these D minus 1 factorial into K power D minus 1 sets, each of size D minus 1, because originally they had size D, each of them had V. We deleted V from the sets, and now we have sets of size D minus 1. And now we have a case to apply our, now we have an instance to apply our induction hypothesis. So by induction hypothesis, this family will contain a sunflower, and now with K plus 1 petals. And now if you have a if I give you a sunflower here, you put back V in the core of this sunflower, and this will be a sunflower for the original family also, right? So if you can find such a vertex V, which I also call a good vertex, if you find such a good vertex, then we are done. So now next we see how we can find such good vertices. And in fact, what one can show is that if I give you a family with large enough sets, then that family either contains a sunflower with K plus 1 petals and an empty core, and such a sunflower can be found using a greedy algorithm. Either that happens, or there always exists a good vertex. In either case, we are happy, because if the first thing happens, we prove the original statement. If the second thing happens, we use induction hypothesis. So let's see why this is true. So let's go to the left side and see, and let's try to design a greedy algorithm to come up with the first case. Let's try to come up with a sunflower with K plus 1 petals and empty core. And a greedy algorithm will start by picking up a set, let's say S1, and now try to pick up a set S2 that is disjoint from S1, if it can, and then try to pick up a set S3 which is disjoint from S1 and S2, and go on. And the algorithm will go on and on until it can no longer find a set that is disjoint from all of the sets that it has already computed. And let this collection of sets, pairwise disjoint sets, be S1 to SR. So now, of course, if R is greater than or equal to K plus 1, then because these are pairwise disjoint sets, you get a sunflower with an empty core. In the other direction, if R is at most K, let's go to the right hand side. So if R is at least K plus 1, then we get the first statement. We get a sunflower with K plus 1 petals and empty core. And in the second case, let's try to find a good vertex now. So when R is at most K, let's go to the right hand side. So we have sets S1 to SR. This was the maximal collection of pairwise disjoint sets. And as I said before, every other set in the family definitely intersects, at least definitely contains one of the vertices which are present in these sets. So let's denote by X the vertices that are present in these R sets. And we know that the size of X is at most dk because R was at most K. The size of each set is at most is D. And now basically you have X many vertices, and we know every set definitely has at least one vertex of X. So now by a simple pigeonholing principle, one can show that there exists a vertex in X, small x, vertex in X, which is present in at least the number of sets that you have divided by the vertices of X many sets. There is a vertex that is present in at least F by X sets, right? Simple pigeonhole principle. And then when you do this calculation, F size is D factorial into K power D, and the size of X is D by K, dk, you get that there is a vertex that is present in at least D minus 1 factorial into K power D minus 1 sets. And this is precisely a good vertex. And this finishes the proof of the sunflower lemma. Again, any doubts? If not, please put a +1. Okay, I mean, if you want, I can pause. Like if you need a few seconds to phrase your doubts, I can wait. Okay, so if that's not the case, let's proceed. So now we have the sunflower lemma, and as I said before, sunflower lemma is in itself is a very strong tool, and it can be used in various it has various applications. And in fact, even in parameterized complexity, its applications are not just limited to the de-hitting set problem. It can be applied to many more problems. Let's see one more example of a problem where the sunflower lemma can be applied. And this is nothing but the dual of the de-hitting set problem. This is called the D-set packing problem. So the problem input is the same. You have a universe U, you have a family of subsets of universe of size at most D and an integer K. But now the goal here is to find at least K pairwise disjoint sets. So if you look at this instance, and if I pick these two yellow sets, now I'm not looking at a subset of the universe. I'm looking at some two sets in the family that are pairwise disjoint, right? So here you have a set packing of size 2, and note that the way D equal to 2 case was the hitting set D equal to 2 case was the vertex cover case. D equal to 2 set packing case is precisely the K matching problem. So again, D equal to 2 case, you can think of it as being given a graph. And if you're looking at K pairwise disjoint sets, and the sets corresponds to edges, so you're basically looking at K disjoint edges, and that's precisely a K matching in the graph. And contrary to vertex cover, which is NP complete, K matching we all know is polynomial time. But now even though D equal to 2, set packing is polynomial time, which is the K matching problem. For higher values of D, the set packing problem becomes NP hard. Okay, so now our goal is to design a kernel for the D set packing problem. And to do that, let's try to mimic the bus rule for the 2 set packing problem first. And even though 2 set packing is polynomial time solvable, like doing kernelization looks like overdoing things, but just to get an idea of the intuition behind why things work for the D set packing case, let's start by the 2 set packing problem, and let's try to design a rule, a reduction rule for the 2 set packing problem. And the reduction rule is as follows. Okay. The doubts? Okay, so if there is a vertex with, if you find a vertex with degree at least 2k in the graph, then the rule says you pick any arbitrary edge incident on that vertex and delete it. So this is the rule, and let's see why this is correct. So this is a vertex with a lot of degree. By lot, I'm meaning it has degree at least 2k. And now I go and decide to delete this edge marked by a red cross. And let's see why this is fine. So of course, if the original graph had a k matching, this graph also has a k. Wait. No, sorry. If they're in the reverse direction. So if the reduced graph has a k matching, then the original graph also has a k matching. But let's look at the forward direction. Suppose I give you a k matching in the original graph, and the problem lies when this k matching uses this deleted edge, right? And now I want to say that if there is the matching in the original graph that uses this deleted edge, then I can always construct another matching which does not pick this edge, but picks some other edge incident to this vertex. And let's see why we can do this. So look at the matching in the original graph. It has k edges. So this matching so blue edges represents the edges of the matching of the original graph now. So it uses this edge that we have deleted, and it might use the edges incident on vertices of the neighbors of this vertex. But now, since it's a matching of size k, if it has already used this edge, then the matching edges can be incident to at most twice into k minus 1 vertex neighbors of this vertex. So which are these vertices? And because this vertex had at least 2k neighbors, one of the neighbors is the neighbors that we had deleted, whose edge we had deleted, and there are 2 into k minus 1 neighbors which already have a matching edge incident on them. There is still one remaining which is not present in the matching, and which is very well eligible to be a part of a matching now. So we can, in this case, we can definitely replace this matching edge, which is crossed, by the matching edge, by an edge just below it, right? So if the degree of a vertex is very large, we know that at least one of the edges can be deleted. One of the edges can incident on it can be deleted. And as we just discussed, this is safe for the matching problem or for the two-set packing problem. And if you just think about it a little bit, you realize that with exactly the same idea for the general D-set packing problem, you can come up with this tool. So now we are again in the set system, and now one can see that if there is a sunflower which has at least d into k minus 1 plus 2 petals, note that for d equal to 2, this is exactly 2k, the bound that we had in the previous slide. So if we have a sunflower with these many k petals, then we can delete one of the sets of this sunflower. So this is analogous to deleting one of the edges for the d equal to 2k's. And one can show that this is safe. And I'll not show this because it's exactly the same ideas as the previous slide. So again, we apply this rule, and when the rule is no longer applicable from the sunflower lemma, we get a bound on the number of sets and the number of elements in the instance. And again, an important point to note here is that the kernel size asymptotically is order k part d, right? So these were the results that I wanted to talk about. So let me now just summarize what we did today. So we saw kernels for basically these 5 problems: the point line covered problem, the edge click covered problem, the vertex covered problem, again, the de-heating set problem, and the D-set packing problem. For the first 3 problems, basically the rules were the reduction rules or the pre-processing rules were designed based on some combinatorial insights about the problem. For the other 2 problems, of course, a combinatorial insight about the problem was used, but this also had to be aided with the tool of sunflower lemma. So we used sunflower lemma, and we also proved it. So we showed these bounds on the sizes of the kernels. What's more interesting is that these simple kernels that we saw, it turns out that all the kernels that we saw today are essentially tight. In other words, if you are aiming to get, you cannot reduce the asymptotic sizes of these kernels beyond what we already see. So for example, we show that point line cover has a kernel with k-square points, it can be proven under reasonable complexity assumptions that this problem cannot admit a kernel with order k power 2 minus epsilon points. Or CLIQUE cannot admit a polynomial kernel. We showed an exponential kernel, and it was pretty simple, but we can't get a polynomial kernel even by designing some ingenious rules. And similarly for vertex cover kernel, size-wise, one cannot do better than 2 power order k square. D-heating set cannot be compressed or kernelized to an instance of size order d power k power d minus epsilon. Similarly for D-set packing. So, but there is a little caveat here. This does not mean that these kernels, there is no scope of improvement in the sizes of these kernels. And the caveat is here that when we say vertex cover does not admit a kernel of size order k square, order k power 2 minus epsilon, we mean that the overall size of the instance, and the size of the instance comprises of both the vertices and edges of the instance, that the overall size cannot be reduced beyond quadratic in k. But that still does not rule out the possibility of having a kernel where at least the number of vertices is linear or subquadratic. Like here the vertices were quadratic, but what about having a kernel where the number of vertices is order k, but maybe the edges are still order k square? Similarly, what about having kernels for D-heating set and D-set packing where maybe the number of sets we can't do anything better than order k power d, but what about having kernels where the number of elements in the family can be reduced, maybe, let's say, to order k power d minus 1. And it turns out that for these three problems, one can actually get all these results that I've marked with the green tick. And in fact, we'll be seeing one of these results, the yellow one, tomorrow. And also, we'll not see the next two results tomorrow, but the tools that we'll see tomorrow can be used to get these results, at least. So this was about the summary. Yeah, one important point here. Note that note that the D-heating set and the D-set packing problem that we discussed, we designed a polynomial kernel for it, but this problem is actually W hard. The set packing problem is W hard. And by which I mean, like if I don't allow the sizes of the family to be bounded by D, then this problem becomes W hard. But if as long as the sizes are bounded by some constant D, then the problem is tractable or polynomial time, has a polynomial, sorry, not polynomial time, it has a polynomial kernel. So this was about the summary. So as I said, tomorrow we'll see an order K. We'll see two basically order K vertex kernels for vertex cover. And we'll see basically these three techniques, the techniques of Crown decomposition, some LP-based kernels and expansion lemma. And we'll see some more examples for these techniques. So that's what we'll do tomorrow, again, in the first session. And that's all that I wanted to say. Just one last thing for those of you who are fresh to this field, maybe if you want to get some takeaway problems to try and see if you follow the arguments that we discussed today. So maybe two good problems to try and solve. I mean, if you're interested, would be the following. So one is the connected vertex cover problem. So this is the same as the vertex cover problem, where the solution, additionally, you want the solution to also induce a connected subgraph. So you want a set of vertices such that every edge is incident on this set of vertices, and the set of vertices should induce a connected subgraph. So we saw that vertex cover admits a polynomial kernel, but it turns out connected vertex cover doesn't. But you can still try to design a connected vertex cover does not admit a polynomial kernel, but you can still try to design an exponential kernel for the connected vertex cover problem. And the way to go about it is just look at the two rules that we had for vertex cover, just try and mimic the rules for connected vertex cover and see where it fails. I'm sure if you see where it fails, you'll get an idea of what you can do to rescue those points, and that will give you a two-part K kernel. So that's a good exercise if you want to do it. And then another problem, you saw this feedback vertex set problem yesterday in the iterative compression session. So let's say I tell you that the input graph is D regular. That means every vertex has degree exactly D. Suppose I give you that. Now, can you design a kernel for the feedback vertex set problem where the number of vertices and the number of edges is ordered d into k. So this should also be doable once you start to see what is the structure of the feedback vertex set problem, the kind of things that you've already seen. And one can try and see if you can get this kernel. These should be doable for those of you who are just afresh to this. So with this, I'll stop and thank you for listening.
All right, thank you so much, Roohani.